Welcome back. So this is the first video where we're starting to explore, we're broadening our understanding of the types of problems and the types of ways we want to solve problems moving forward. So up until now, we keep talking about completeness and optimality, right? We've kind of held optimality as this golden standard, this requirement of what we're going for with our algorithms. Now, optimality is obviously very important. In many situations, we care about the cost of our solution. That is our main objective. But this is not always the case, right? So in this video, we're going to discuss the idea that sometimes in some applications, we may need to give up on optimality, right? And we're going to be looking and searching for suboptimal solutions, but we're going to do this faster, right? So suboptimal solutions are often necessary in these kind of domains where we don't have time to find the optimal solution. What's far more important to the player, to the experience of the user, is to return a path. Return a path. We want it to be the best path that we can find, but sometimes it's much better to get any path rather than to essentially fail, right? To have this critical failure, to not return a movement direction to our robot, to our player, to the user. So this is extremely common in many application areas, right, where time or computational resources are extremely limited. So very often in video games, right, your movement system, first off, I guess technically your video game preferably runs on a potato, of course. And even if it doesn't, most of the computational time, of course, is dedicated to graphics rendering and so forth, and not to the pathfinding system. When a player clicks move to this location, the player better start moving instantly, right? No one wants their player to stand still for a second as it computes the optimal solution and then start moving. No, you need your player to start moving immediately. So this is obviously very important in a lot of real-world robotics scenarios and applications as well, right? If you've got some UAV flying around, it has to respond dynamically to obstacles and threats, right? If you're about to run into a wall, you can't take a second to find the optimal way around it. You gotta dodge that wall, you gotta dodge that bird. So yeah, in many situations, it's more important to return a path than the optimal path. But obviously, solution quality is always still important. So we don't want to throw away the idea of solution quality altogether. What we're going to be looking for and talking about in this video is essentially the trade-offs that we can make in the solution quality and the time it takes our algorithms to search. So as an aside, some of this is going to lead on to the next video in this series, where we start to look at anytime search behavior, which is also another really important aspect of search, right? So when I'm saying we don't care about getting the optimal solution, well, oftentimes, right, when the player needs to start moving, well, why don't we find a bad path quickly, and then we can iteratively improve the path thereafter. So stay tuned for that conversation as well. I just wanted to preface that because we're not dealing with this idea of iterative improvement here. We're talking about problems where it's like, hey, I just want a really fast path. I want it to be pretty good, but I need it quickly. And so in returning to then types of suboptimality, we can classify the types of algorithms and the properties that algorithms might give us, because they're a whole different field and ecosystem of algorithms that meet each of these types, but they're all very different, right? And you'll apply them to different problems, and it always depends on the original problem and what you care about most. So there are suboptimal algorithms where it's just speed that's important, right? You want to give me the fastest solution. I need it now. I don't care much. I don't care about the quality at all. I don't even care, technically, obviously I care a little, but you are allowed to not return a solution, okay? So these will be incomplete, unbounded. So, hey, we might not find a solution at all. Even if we find a solution, its quality is completely unbounded. Who knows what quality will return. Now, the benefit of this is that it is very fast, right? We are blindingly fast oftentimes, but of course the downside of that is that we might fail. Okay, sometimes maybe that's an acceptable situation. These algorithms absolutely exist, and they're usually extremely simple. They're just going to build some form of like minimum spanning tree, something like this, try to connect up to the tree. Sometimes they fail, unlucky, but it's so fast that, hey, maybe you can just spin up another thread. Then the second version of this is that, okay, well, of course, then how about even if it's still unbounded, but this time it's complete. So some algorithms can spend a little bit more time, but still be extremely fast. I'm still going to write very fast. But essentially now it's like the solution quality is still unbounded. So variable, very variable. Solution quality. Okay, so these kind of algorithms are still very, very fast. We can like do a little bit better, right? You reason over the environment to make sure that, hey, the search space, if we exhaust it, will give us a solution. Often still very fast, but trade-offs. So I think this is often more times used than number one, but you know, it always, of course, depends on your application, your resources, things like this. Yeah, so these two are both unbounded. That's their key characteristic. You don't have guarantees on the solution quality. We know that even though we're giving up on optimality, I think what we all can see is that it would be much nicer if our algorithms at least gave us an idea. The quality of the solution was bounded. It was predictable. It was controllable. You can use a threshold or some parameterized value to drive how much suboptimality you are okay with. And so that's the exciting aspect of this. So then there are the other versions of this algorithm, which is bounded suboptimality. And so there are different versions of guarantees that we can have on solution quality. But the first is this idea of, right, you're okay with some form of relative suboptimality. So some linear relationship. You can essentially like a multiplicative relationship between your optimal cost, right, and then the cost of the solution you may want to return. So this makes sense, right? You're saying like sometimes, hey, I would prefer my algorithm be faster, but please don't be more than 2 times worse, right? I'm okay if the path is 2 times longer, but that's it. If it's longer, the player will be upset. And so this is what we call relative suboptimality, where the cost of your solution C is less than or equal to some, we're going to call it a weight, W times the actual optimal cost, the optimal cost C star, right? So, hey, if I'm okay with a 2 times worse solution, 3 times worse solution, 2.5 times worse solution, right? We often say that in these situations, W has to be greater than or equal to 1, right? Where obviously you can't be better than optimal, so it's undefined when you're obviously essentially dividing instead. Maybe I'm okay with a 1.2 times worse solution, and you can kind of tune that perhaps in practice. Then finally, the other version of this suboptimality is simply additive. So you can do the same thing, right? So essentially you can choose the actual cost threshold, cost difference itself that you're okay with. So in this situation, the cost is essentially less than or equal to the true cost plus some form of epsilon, right? So where epsilon is, again, technically, where of course epsilon also should be a positive number, right? You can't do better than optimal. Okay, so this concludes our initial talk on the ideas of suboptimality. We're making these trade-offs. Well, let's quickly then jump over to the first of our algorithms that build upon A star, we'll see again the beauty of A star in all of these different versions of the problems. So many of our algorithms just end up essentially adding letters to A star. So we're about to look at weighted A star, W A star. This is the version of A star where we can modify the algorithm to make this direct trade-off in terms of the suboptimality that we want the algorithm to return.